Hello students, we left off 2 days ago talking about work, and work is related to our moving objects. In order for us to get something to move, we have to apply a force to it. Now that force might be us pushing a box or pulling a box across the surface with, let's say, 10 newtons of force. If the object is moved a distance parallel to the applied force, a distance of 10 meters, well, to figure out how much work that would be done in this case, you'd multiply the two together, and we come up with the work done is 100 joules worth of work. If this object were to be, let's say, pulled at an angle such as this, right? And let's say our applied force this time, just to make the math easy for me, if it's 5 newtons, all right, if our distance moved is in this direction, our distance still is 10 meters right here, well, there's a small problem with it that my direction of the applied force is to the upper right, but my movement is to the right. So only a portion of that 5 newtons of force is actually going to move my box to the right. So we can't say that the work done would be 5 times 10 because not all of that force is being used to move the object. So what do we have to do instead? We have to use some trigonometry. So we would need to know what this angle is right inside of here. This would be our adjacent side here. And why are we not looking at the upward force right here? Because if you're pulling upwards, that's not going to cause the box to move to the right. It might cause it to move up into the air a little bit, but it doesn't cause it to move to the right. So the reason why I chose this 5 newtons acting like this, because if this is a right triangle, this side would be 3, and then the adjacent side would be 4. All right, so our force, once we would calculate this, we would actually have to put in here times cosine theta. So the working out of our problem, you'd have 5 newtons times our distance of 10 meters times cosine, and then we'd have to get that value of our angle. So we would take cosine theta, we go inverse, take cosine, let's go 36.9, let's say, degrees. That's going to be about the right angle for that, I believe. So if we put that into the calculator, you have 5 times 10 times cosine of 36.9 equals, we'd have only a only a amount of work done right here. Our work done would only be roughly, I'm going to round it off, 40 joules worth of work done in this case. All right, so you can see because we have less force being applied, see it's a shorter force, it's less force being applied because some of that is pointing upwards. Because we have less force being applied in the direction of movement to the right, we get less work that's going to be done. All right. The only other situation that we might have is if we're going to lift something up off the Earth's surface like this. Then the only difference would be we'd use the weight of the object, and then we'd multiply that by the distance if we were going to be lifting this straight up, our distance. Okay, so that's the only thing that would differ in that scenario. All right, so that's our work. The other term that we had talked about yesterday was power. Power is the rate at which work is done. So if power is the rate at which work is done, we're going to have work divided by time. All right, now with our two scenarios from above, let's say that we take our 100 joules worth of work. All right, if we take that 100 joules worth of work and we say that it's going to take 10 seconds, just to make the math easy for this. If it's going to take 10 seconds to accomplish that work, well, the power output of this, we would have 10 watts. If we had the same amount of time put into moving the box on the right, you only did 40 joules worth of work, remember? Because it was at an angle. Here, if we divide it by 10 seconds, you can see that the amount of work is less, same amount of time, so that means the power is less as well. So the same amount of time, different amounts of work, different power outputs. All right. What we're going to look at today is our next topic. We're going to be looking at work in motion. We're going to look at the position of our objects relative to the Earth's surface. We'll look at mechanical energy. Mechanical energy, I was kind of hitting at it there. Our first type of mechanical energy would be potential energy. Potential energy, anything that I highlight here, you're going to need to have in your notes. So our definition is what we need to have for this. Potential energy is stored energy. It's energy that's held in the readiness for us to be able to do work. So if you have a bow and you pull back on the string, well, that you are doing work, putting energy into that string. You're storing energy in it, and then it has the potential to do work. If you have a rubber band, you pull back on the rubber band, you are storing energy in the elastic potential form, and if you were to release it, it would be able to do work. Another type of potential energy is related to what I kind of alluded to a little bit ago, gravitational potential energy. Gravitational potential energy is related to the position above the Earth's surface. If you have a dumbbell and it's resting on the Earth's surface, right now this dumbbell has zero joules worth of potential energy because it can't fall anymore. It's not above the Earth's surface, it's on the Earth's surface. If you take this dumbbell, however, and we put a little bit of work into it, now notice I said that we're going to put work into it to raise it up. If I put 10 joules worth of work into lifting this up, how much potential energy do I have as it's being held at the top? I would have 10 joules worth of potential energy. So what we see here is that work, when we're looking at gravitational potential energy, the amount of work that I put into it equals the potential energy. All right? And we could even, sometimes what you see is people put GPE to help identify what it is. I believe the actual appropriate variable that people use for this is U. We're not going to use that. We're just going to use GPE because that makes sense, gravitational potential energy. And you're going to notice our unit of measurement, the joule. It's the same thing, energy. It's the ability to do work. All right, so let's come over here. Our formula to determine what the gravitational potential energy is, first off, it equals the work done. You apply some work into lifting something up. So you have a mass that you're lifting, and again, anything highlighted you want to have down. So potential energy equals the mass that you're lifting. Well, if you're lifting it up, you're going against the pull of gravity. All right, so we'd have to have that in there. And then if we're trying to figure out how much work you did, well, you need to know how high you lifted it. So you're going to need to know the height. So we can abbreviate it. Oftentimes you're going to see it like this in a textbook. Myself personally, how I write this out, I put GPE equals, and then I say mass times gravity. That's how I do mine. And then we have distance. So either way, there's not a right way or wrong way to label these. It's just what works for you. Okay? So let's look at our first question. We have, does a car hoisted for repairs in a service station have increased potential energy relative to the floor? All right, make your choice. Well, If the car was raised, that means work was done onto it. If it has work that was done onto it, lifting it up, then yes, most definitely it does have an increase in potential energy. Here we have a couple of scenarios. Let's put in some numbers here to figure out how much work is done in each one of these. All right, you're going to need to be able to do this yourself, so I would suggest you write down a couple of these problems here so that way you know how to do it yourself. So this ball right here, this thing has a weight of 10 newtons, and it's going to be raised a distance of, right over here, 3 meters. So our work done is 10 times 3. So our work here is 30 joules worth of work. So that means that as it's resting at that point, that's how much gravitational potential energy it has as well. Now, in the other case, we're using an inclined plane for this. Now, with an inclined plane, the height still is 3 meters, okay? But an inclined plane is a simple machine. Simple machines multiply the effort force that's going to be put into your system, making work a little bit easier. It doesn't multiply the work done, it just multiplies the effort force, so it makes your life a little bit easier. So we need to figure out from this what our mechanical advantage would be. How many times does this inclined plane make your work easier? So with an inclined plane, what you're supposed to do is take the height, all right, or length of your inclined plane and divide it by the height. All right, so if you take 5 divided by 3, you're going to have a mechanical advantage of 1.7. Now, that means that you are going to have to put less effort into lifting this object up because this ramp is nearly doubling the force as you roll the ball uphill. All right, so what does that do to this force right here needed to lift it? Well, we'd have 10 newtons. Remember, it's almost cut in half where this simple machine is increasing your effort force. So you take that 10 and we're going to divide it by, you have 10 divided by 1.7, let's say. So here, instead of applying the full 10 newtons of force, you are only having to apply a force of, because we divided this by 1.7, you have 5.9, and I'm going to round it off. All right, you're only going to have to apply 5.9 newtons worth of force into this ball, pushing it uphill like this. Now you might say, well, wait, 5.9 times 3, that doesn't get me the same amount of work, 30. But we're not lifting it up straight 30 or 3 meters, you're lifting it 5 meters long. So if we multiply that by 5, if we multiply that by 5, what do we come up with? We end up with 29.4 and some change. Oop, hold on, that looks ugly. We got 5 meters. That comes out to be 29.4. Now you might say, wait, that doesn't come out to be the 30 joules. Didn't I just I rounded this number off, and then I rounded this number off? So that's why this didn't come out perfect. But if I didn't round any values off, what would this be? 30 joules worth of work. 30 joules worth of work. Over here, you know what we'd have? 30 joules worth of work. 30 joules worth of work, 30 joules worth of potential energy. So regardless of how you get that mass up the 3 meters, it still, in every one of those cases, will have the exact same potential energy. All right. Once that ball is at the top of the ramp, well, what could it do? It could fall. And if it falls, it's going to have some kinetic energy. Kinetic energy is energy in motion. Kinetic energy, it's going to depend on the mass of the object and the square of its speed. This brings into light a formula. A formula for this, we're going to use kinetic energy equals 1/2 times the mass times the speed. Or a simpler way to write that would be KE equals 1/2 mv v squared. Now that does have some implications to it, because if the speed of your object is doubled, what happens to the kinetic energy? If we've plugged in some numbers, we would find that the kinetic energy is going to be quadrupled every time that you double your speed. That's why it's so important when you're looking at speed limits, why you shouldn't exceed the speed limit to the extent that some people do, because if you are doubling your velocity inside of like a school zone, the amount of force needed to stop you, the amount of kinetic energy is quadrupled, so you're going to require a greater amount of time to stop you, okay? There's only so much friction that the tires and the road can provide, and if you can't increase the amount of force, then you're going to have to increase the amount of time necessary to stop you, all right? So, next question we have, must a car with momentum have kinetic energy? All right, make your choice. If something is in motion, momentum is the property of a moving object, and if it's in motion, then it has kinetic energy. So yes, it does. Of course it does. All right, so kinetic energy. Kinetic energy and work of a moving object, they have to equal each other at different points. All right, so what I'm going to do, I don't need you to write this down. What I want you to understand is there is a relationship between the amount of kinetic energy and the amount of work that's being done on an object. There is a relationship. Now that relationship is in the form of this equation right here. So this I would like you to have written down. All right, so if we're looking at that relationship, you have force, the net force, the sum of all your forces, times the distance. That's going to equal the amount of kinetic energy. What we're talking about here is if we take that dumbbell. We don't have to have anything real specific. We have this dumbbell that we're going to be raising up into the air. You have the weight of the dumbbell times the distance that it was raised up off the surface. That will tell us how much potential energy, gravitational potential energy, is stored in that particular object. Once that object is released and it falls, what's the amount of kinetic energy that it's going to have at the bottom? That's going to equal what we had in terms of gravitational potential at the top. All right, so let's see just a number here. If we had 100 joules worth of potential energy at the top, how much kinetic energy would we have at the bottom? We'd have 100 joules worth of kinetic energy at the bottom. So those two variables, they are equal to each other. That's kind of what I'm trying to get at here, okay? So that brings light our work energy theorem. If we have a gain or reduction in energy, it's the result of work. In order for you to gain energy, gravitational potential energy, you have to put some work into it. If you want to get something out of it, you have to release it, but when you release the object from a certain height, you're going to lose potential and gain kinetic. So we can say that those two items are related together. All right. And again, implications. Implications, if we double that speed, then that's going to require 4 times the amount of work in order to stop that car. Okay, so you double the speed of your car, there's only so much braking force that the tires and road can perform. So if you double the speed of your car, you're looking at drastically increasing the time that it's going to take for that car to stop. All right. Question. We have consider a problem that asks for the distance of a fast-moving crate sliding across the factory floor and then coming to a stop. The most useful equation for solving this problem is, let's make your choice. It should be where we are given the distance is our unknown variable. If we're trying to stop it, we don't have distance in any of the other ones. Okay? So we got to have that distance inside of our formula. Next question. We have the work done in bringing a moving car to a stop is the force of tire friction. Remember, that's a constant, right? Unless you change your tires and get wider tires or something with more aggressive force, there's only so much friction that's going to occur between, or I guess we could have a change in the surface if it's wet outside or leaves or icy out, then the friction's going to change. But let's not get that deep into it. So to stop is the force of tire friction and stopping distance. If the initial speed of the car is doubled, the stopping distance has to do what? All right, is make your choice, and what we see here is that it's none of those. Remember, if you're going to double the speed, then the kinetic energy is going to quadruple. So you're going to be looking at 4 times the stopping distance needed to stop your car from traveling at 25 miles per hour versus 50 miles per hour. All right, law of conservation of energy is what we've been talking about here. See, when we had the example of the dumbbell at the ground levels where we're going to start this at the ground level right here, there is 0 potential energy in it. It can't fall anymore. It's on the ground. And if we raise this dumbbell up into the air, all right, it's going to be right up here now. Okay. So if we raised this up and we now have 100 joules worth of potential energy, how much work did I put into raising that up? Well, I put 100 joules worth of work into it. Now, as it is resting at the top here, how much kinetic energy does this have? At the top, if it is not moving, it has 0 joules worth of kinetic energy. It's not moving, 0. The dumbbell is now released. So let's choose a different color. As it's released, if it's halfway down, how much potential energy does it have? If it's halfway down, we don't need to put a formula to this. If it's halfway down, it has half the potential energy. And if it's halfway down, how much kinetic energy does it have? Well, it would have to have 50. We have to have a conservation. We're not going to create or destroy anything. All right, now, continuing the moment right before it hits the ground, how much kinetic energy does it have right before it hits the ground? It's going to have 100 joules worth of kinetic energy. So the result here in that law of conservation of energy is that energy cannot be created or destroyed. It can be transformed from one form into another. So we can change it from potential energy to gravitational potential energy to kinetic energy. But the idea here is that the total amount of energy never changes. And you can see that in my example. Here is another example of this. We don't need to put a lot of numbers in here. All I'm going to say is at the bottom, the potential energy down here, potential. We have potential energy down here is going to be 0. Up here, let's say our potential energy is 500. If we have a conservation of energy, that means the kinetic energy just before it hits the pile driver here, it's going to be 500 joules worth. Okay, conservation. What we're going to do is look at problem set 3. Okay, problem set 3. If you want to do these on your own and not have to watch the rest of the video, then great. Go ahead and do that. But if you need some assistance, what you'll need to do is follow along with the video, fill in your information, and I will help you with some of it, but you have to actually put the numbers into the calculator yourself. I'm just going to help you with the setups. All right, so question 1. Question 1, problem set 3. There are 5 questions, so it's not much. So we have 5 questions to work out. Number 1, It says you have a mass of 200 kilograms. It says that it's going to be lifted a distance of 10 meters. It says find the potential energy of this system. Potential energy equals, now it's gravitational since we're lifting it up. And if it's gravitational potential energy, we have to have gravity in the mix. Okay? So gravitational potential energy equals the weight of our object, that's 200 kilograms, times gravity. So we have the weight of our object being lifted, and we're going to multiply that by our distance of 10 meters. So I should have put our formula in here. I kind of failed with that. So we have MAGD. All right. You have to plug these values into your calculator, and then you're going to tell me how much work was done in lifting it, which in turn tells us how much gravitational potential energy is stored in that pile driver. Hammer of a pile driver. So let's go to question 2. Question 2 here says that you have a 60 kilogram shell, so mass equals 60 kilograms. It is shot straight up into the air, and it goes a distance of 400 meters. Says, what is the potential energy of this? All right, so potential energy, since it's being shot straight up, we're looking at gravity. Anytime that you have gravity, you have acceleration, 9.8 meter per second squared. All right, so this time I'm going to put the formula in here, not fail. So you have your formula. What you have to do is you have to plug in your variables. All right, so you have to show your work here, and then put it into the calculator, and then give me the answer in terms of joules. Now that is part A. This is part A. Part B is if you change your distance to be 200 meters instead. Well, from the notes, if you followed along with the notes, I talked about something falling half the distance and how much potential energy it would have. So you technically would not have to do this whole thing again if you understood that part in the notes. All right. Now, if you didn't understand that part in the notes, well, you're going to have to plug in your numbers into that formula to get your value for this guy right here. Okay. So one way or another, you have to show what the answers are for that. Let's go to question 3. Question 3 says that you have a person who weighs, all right, so that's weight. Weight is a force of 630 newtons, and they're going to climb a distance of 5 meters. It says, what work does the person do? The person, if we're looking at work is force times distance. So you have to put in your substitutions, and then you have to give me what the work done would be right here. It says for part B, what is the increase in potential energy of this person? Well, if this person is going to be lifted up 5 meters, and we know how much work was done to lift that person up, shouldn't you know what the gravitational potential energy of that person is? Yeah, I think so. Okay. So let's go to the next one. We have number 4. We're getting close to the end here. We have number 4. It says that we have to find the potential energy of a mass. The mass is 10 kilograms. And it's raised a height of 20 meters. So if you're trying to find it's being raised, so that's gravitational potential since it's being raised. If you have G, gravitational, you got to put acceleration due to gravity in on this. Okay? Now, I said I was going to give you less and less, so you have to figure out what the right formula is. You'll have to substitute in your information, and then you have to provide the answer right here. Don't put in squiggles. I've had people do that in the past. You have to fill in the information. You can't just put down squiggles, all right? So let's go to a new page here. we've got the last one, number 5. Number 5, it says, in order to charge the plates of a small storage battery, a hand generator is cranked a total distance. All right, so we have distance equals 250 meters. The average force, so we're going to have force equals 120 newtons. In turn, it says how much work is done. All right, so you have to find that formula for work, plug it in, and then substitute in your variables to get what the correct value, what your answer would be for this. Okay, so you got to plug in your missing information there. It says, that's for part A. Part A, by the way. Part A. So it says part B says if the work was done in 1 minute, what is your power? All right, well, power equals, and I'll give you a little more help with this one, work divided by time. And it says the time here was 1 minute. All right, 1 minute. You don't want to use minutes, okay? You want to use seconds. You guys can do that on your own. We will use our value from before and plug it in, and then you're going to use your time and plug that in to get part B. So part B is right there. The last part, part C, don't overthink this. This light bulb is going to use 10 watts of energy for every single second. All right, so if we know how much power we have, okay, if you know how much power we have, and you know that you're going to be taking away 10 watts from it for every single second, you should be able to figure out how many seconds that light bulb is going to be lit for. All right, so we have all of your setups. Everything is ready to go. All you have to do is make sure that you have answered everything. You take a picture of your work, you submit it to your lesson on Schoology, and after you do that, you want to put your answers to all of these things right here. You want to put all those answers into the homework check. If you have questions, make sure, as always, that you ask for some help. All right? Take care.